Right, we are going to talk about the very basics of chemistry today. Biochemistry is really important in our understanding of overall biology. It is based in chemistry of molecules interacting. So we're going to learn the basics right now. So early chemistry back in the day believed in one element, and we have my little funny joke over here. Dirt. Later chemists believe in four elements: air, earth, fire, and water. Various combinations of these produced various compounds, was the belief. We have since found out that all matter in the universe is composed of what we call atoms. Atoms are the smallest structures. When we are talking about life, we're going to be talking, you already should have learned in last class, that life is it's a hierarchy, sorry. And the smallest component of life is atoms. And we're taking a look at the structure of atoms right now. Atoms compose elements, and elements are composed of one type of atom, okay? So what's weird is that atoms are mostly empty space. They have electrons, which are really small, and they float around in these, I call them orbitals, outside of the nucleus. They're negatively charged and have a negligible mass, so their mass is essentially zero. Inside of the nucleus, we have the neutron and the protons. So electrons move in orbits around the center of the atom, okay, in relatively distinct areas called energy levels. If you've taken chemistry, you've already learned how to calculate or learn where electrons stay. I'll be teaching you a much simplified version of that, or I call it the biology version of learning and understanding where electrons are in their orbitals or in their shells, because it's really important to understanding how bonding occurs. The further from the center of electron, the more energy it has. Electrons, and therefore atoms, can gain and lose energy, and they do this by moving between energy levels. And eventually what you'll learn is that when electrons move, so does energy. So as we talked about before, atoms have a nucleus which contain protons and neutrons. Protons are positively charged and they have a mass of 1. The number of protons in an atom's nucleus is what determines what element it is. Neutrons have no charge and are therefore called neutral and have a mass also of 1. Okay, so here's a summary of our subatomic particles. Electrons charge negative, protons positive charge, okay, and neutrons have no charge. All right, so this is going to become important to us. Chemical elements are represented on the periodic table using the following format. We have our element here. We're looking at carbon. Carbon happens to be biology's favorite element, one of them. Okay, we're looking at its mass number, and now depending on what periodic table you're looking at, a lot of times the mass number can go underneath and the atomic number can go up top, okay? A lot of times, probably the one that you'll see with me, these two will be switched, but you'll always know. The atomic number tells us how many protons there are. The mass number tells us how much the molecule weighs, and we talked earlier about the proton weighing 1 and the neutron weighing 1 and the electrons weighing nothing. So it makes sense to us that the atomic number, the mass number, is how many protons and neutrons that we have together, okay? So the element name, the atomic number, is a number of protons, okay? And remember, it's the number of protons which determines which element it actually is. Okay, so the mass number is the total mass of an atom, which is measured in AMU. It's the same as the number of protons. And there's always, if there's no charge, there's always the same number of neutrons and protons together because, yeah, well, that's how it works. You can calculate the number of neutrons in an atom, like I said before, by subtracting the atomic number, which is the number of protons, from the mass number to tell you how many neutrons there actually are. The mass number can change without changing the identity of the element, okay? And that's called isotopes. Atoms have the same atomic number and different mass numbers. We call them isotopes. They're atoms of the same element with different numbers of neutrons, okay? They react chemically the same as the normal form of the element. They are frequently radioactive, is what that says there. Okay. So we really like to focus a lot on the interactions of matter and how things bond. And in the next lecture, you're going to be learning about water and the interactions between those elements are important. But in all of biology and all of biochemistry, the interactions of these atoms are extremely important. So atoms interact through what we call chemical bonding. Okay, the process is determined by the number of electrons found in the outermost energy level of an atom. It involves a transfer and sharing of electrons between atoms. And we're going to talk about covalent and ionic bonding, but for biology, we tend to focus most on covalent bonding. So here's the rules. Atoms in a neutral state have an equal number of protons and electrons. And for us, we often don't deal with atoms that aren't neutral in biology. So most of the time, if you don't see all of the time, if you don't see a charge next to the element, there is the same number of electrons and protons. Atoms fill up their energy level from the lowest to the highest, so they rarely what we call skip levels. The first energy level, and this is important, and we're going to be doing some work in class on this so you can understand it. The first energy level can only hold 2 electrons. The second and all higher energy levels, for our purposes, only hold 8 electrons. Okay, those numbers are important. Atoms seek to have a full outermost energy level. So one of the things I like to say is 8 is great. As a non-chemistry person, stupid little sayings like that help me remember things that are important. So all chemical reactions, they happen just to accomplish this full outermost orbital. So that's really important to remember. So let's just take a look at what we're seeing here. So we're taking a look, and we have 2 electrons in the first one. And then you can see 1, 2, 3, 4, 5, 6, 7, 8 out here. 1, 2, 3, 4, 5, 6, 7, 8 out here. This has a full outer orbital. This is not going to want to react with anything because it's already full. Okay? When a chemical reaction occurs, atoms gain, lose, or share electrons. Atoms always want to have their outer level full, like I said earlier. When an atom has a different number of protons and electrons, we call that an ion. Okay? If an ion has more protons than electrons, then it's positively charged. If an atom has more electrons than protons, it's negatively charged. Atoms of the opposite charge are attracted to each other. Opposites attract. There are 3 types of chemical bonds. I'm going to briefly go over ionic. I'm probably going to ignore metallic. In biology, we're dealing mostly with covalent bonds, and we'll talk about that. Okay, so let's just really quickly talk about ionic bonds so we understand the difference. Ionic bonds form when one atom gives one or more of its electrons to another atom to complete their outer orbital. Okay, and this is just showing you NaCl. This results in one positively charged ion and one negatively charged ion. Since opposites attract, they come together and they're going to bond because of that. And NaCl, just so you guys know, is table salt. Okay. Covalent bonds are the ones that we deal with, okay? And this happens when we 2 atoms share one or more of the electrons between them. Okay, and we're going to really highlight this when we talk about water, but we'll take a look here. Sorry for the beeps.
Someone from IT come back to the main office, please?
Anyway, there's 2 types of covalent bonds that we deal with. Nonpolar covalent bonds form when 2 atoms share their electrons equally. A polar covalent bond occurs when 2 atoms share their electrons unequally. And that will happen when you have an element that is more electronegative, meaning it attracts the other electrons to it. And we talk about that in great detail later on. Okay? They can share more than one electron between them, forming double and triple bonds if they need to. Okay? A molecule is a group of 2 or more atoms held together by covalent bonds. So this is kind of just our summary of we care more about covalent, but we have these 2 atoms that come together. They're sharing. They each need 1 electron in their outer orbital, so they share these 2. And covalent bonds are a lot stronger than ionic bonds as well. And here we're taking a look at our ionic bonds. We're stealing an electron, but they're attracted to each other because they are opposites. Okay. we need to discuss chemical reactions, as this is something that we do talk about. A chemical reaction is whenever a chemical bond is formed or broken. So there's two types, sometimes three, of chemical reactants. We have reactants, substances existing before the reaction, so reactants over here. They're always on the left side of the arrow. Products, substances existing after the reaction, okay? And then a catalyst, which is something we get into with much greater detail later on in the semester. Substances which speed up the rate of a reaction. There are substances that they're usually always proteins, but there's also RNA, but they always are speeding up these chemical reactions. Okay, chemical equations are a shorthand way of showing chemical reactions. It separates the products and the reactants. I was just showing you one on the previous slide. Usually follow the flow of energy. Rx or Rxn oftentimes is a way to abbreviate reactions. They naturally occur when they release energy, and that's called exergonic. They can, however, occur when energy is added, and we call that process endergonic, and that's something that we discuss later on. Chemical formulas show the number and type of atoms in a molecule. So, chemical formula for water, H2O. So we have 2 hydrogens, 1 oxygen. Structural formulas we'll use to graphically represent. Okay, it's useful in visualizing how chemicals react and form new ones. So this is our structural formula that we're taking a look at here. I think that I'm just not, I'll touch on this briefly. This is something that we're going to spend more class time on. Okay, so we're looking at the difference between the structural and the chemical formula. So we have water, H2O, and this is how it's depicted. We will talk about the bonding in water and why it looks like this. Carbon dioxide, methane, glucose. Okay, glucose is a ring. All right, and that's going to be it for this particular lecture.